Okay, so we've kind of talked about Newton's third law a little bit here and there, especially when it came to normal force and friction and all of that kind of stuff. But today we're going to look at it for its own sake. Okay, there are a few details that we'll need to go into, but here's the good news. There are no new formulas. Newton's third law, when it's in problem form, is really Newton's second law question. Okay, it's still about a sum of all forces. Okay, the only thing that's different is trying to figure out which forces are acting in a pair. Okay, and that's the big thing about Newton's third law, is that all forces act in pairs. That's why it's point number one, okay, for today, right? Is that all forces act in pairs, because every action has an equal but opposite reaction, which is the most often misapplied law there is in science. It's always put into some social context, okay, where you say something awful to somebody and they smack you across the mouth for saying it, okay, and then you're like, well, every action is equal opposite. No, okay, that is absolutely not where that law applies. You said something terrible, okay, and you probably shouldn't have. This is only a physical law. Okay? And that physical law says that if you do something to something else, it's going to do it back. Okay? This is why, not that any of you would do this, okay, but if you were to, let's say, punch a wall, you're going to break your hand. Because as soon as you punch the wall is going to punch right back. Okay? Whatever force you exert on the wall will exert back. Even if you succeed in going through the wall, okay, it is still going to exert the same force back on your hand. And the acceleration experienced by the tiny little bones in your hand, which are not big and have very little mass, okay, is going to be very large, and that's not good for them. Okay? And then you'll wind up with a broken hand. Okay? Meanwhile, the acceleration experienced by the wall will be quite small, as the wall's mass is quite large, okay, by comparison. So this is the thing that throws people off about Newton's third law and why they think it's not applying in a situation. They see two objects of very greatly differing mass exerting a force pair on each other. And they see one have a huge change and the other no change at all. And they say, well, the forces weren't equal. And the forces were absolutely equal. What was different were the masses of the two objects and their resulting accelerations. So this goes back to the smart car versus semi-truck example, okay, that we talked about before. If a smart car and a semi-truck had a head-on collision, the force exerted by the smart car on the semi-truck is equal to the force exerted by the semi-truck on the smart car. Those two forces are equal but opposite in direction. Okay? Now, the result for the smart car is considerably different than the result for the semi-truck. Would you agree? Because their masses are different. Okay? When it comes right down to it, Newton's third law would be, okay, force on the truck equals negative force on the smart car. Okay, which means the mass of the truck times the acceleration of the truck equals negative mass of the smart car times acceleration of the smart car. Okay, since the masses are different, the accelerations have to be different. All right, so a small mass means a big acceleration, and a big mass means a small acceleration, which is why those two things can be written equal. Okay, everyone kind of follow what I mean there? Okay? All right. So, normal force. We've talked about normal force already. It's that reactive force of any object when another force is exerted upon it. Okay? If I push on the wall exerts a force back on me. That's still a normal force. It doesn't have to be the ground. Okay? Normal force is any reactive force to another force. Okay? And then obviously, third point we've already talked about. Okay? Questions so far? So, if you're in a football game, okay, and you're on the offensive line and defensive line, okay, and you're facing your opponent like you see in the picture here, okay, ball is snapped and both lines crash together, okay. Now, if you hit somebody first, okay, do you win? Not necessarily. Okay, I mean, I've seen sometimes, like especially in hockey, where somebody lines up another player and they're gonna just lay this big hit, and the person who initiates the hit actually ends up worse for wear. Okay, and it's usually because they picked somebody bigger. Okay, so even if you initiate the hit, if the thing you hit is bigger than you are going to feel more acceleration. Now, to do with injuries and hits in hockey and in football, it also has to do with whether you're prepared for that force or not. Okay, if you're not prepared or it's a blindside hit, you are going to get hurt. Okay, mostly because you don't tense your body and get ready for it. Okay, but when it comes right down to it, it is the smaller mass that is going to experience the greater acceleration. But the forces are always equal. Okay, whatever force one line exerts on the other, okay, that is the line forcing, or the force that the other line exerts back. The forces are always equal. Okay, everyone with me on that? It's crucially important that we understand that those forces are equal. Okay, and we call that an action-reaction pair. Okay, so any forces that are equal and opposite are an action-reaction pair. Okay, this is also how a balloon works. So if you've ever blown up a balloon, okay, and then you let it go and it goes all around the room, okay, what's happening there is when you blow up the balloon, okay, the air inside pushes on the balloon. And what does the balloon do? It pushes back. Okay? If you let go of the balloon, that pushback force forces the air out. Okay? And that's what propels the balloon around the room. Okay? This is the same principle used for rocket engines. Okay? You have an ignition tank, basically, where the ignition occurs. Those gases expand rapidly, and they are forced out. Okay? So they push on the rocket, okay? And the rocket pushes back. That's why the gases are expelled, and the rocket is propelled forwards, or up, okay? As the case may be. All right? Okay. So, would you be able to pull this off if you're in the boat? Okay, so you push off and you realize, oh crap, I left the oars, and now you're kind of screwed. So you're going to just run down the boat and jump onto the dock. Did you do it? Why not? Okay, boat's going to move under you. So because I'm running forward, I'm pushing the boat backwards. Okay, but what is the boat doing to me? Right? So if I run down the boat and then I jump, I push on the boat. But the boat pushes me. As long as I do it right, and I'm not obviously too far from the dock, okay, I won't leave my chiclets in the dock. Okay, you guys know what I mean when I say that? My chiclets, yeah. Okay, so if I run down this boat, okay, when I'm running, if I, just put kind of one foot in front of the other, yes, okay, the boat is going to move backwards a little bit, but it's going to propel me forwards. And when I make that last jump, okay, I'm going to be propelled forwards by the reactive force to my force acting on the boat. I can better my odds by directing my force which way? Well, I would direct my force downwards a little bit more so that the reactive force would be upwards. Here's how that works in my advantage. If I just push straight backwards, I'm only acting on the mass of the boat. But if I push downwards, now I don't just have the mass of the boat, I have the mass of all the water under it. Okay? Is the boat going to go down as much as it would go backwards? No, because now I'm pushing on more mass. If the boat plus the water under it, okay, I'm going to get more of a boost upwards. Now, that means that my vector is going to be a bit more upwards than it is forwards, okay? But I'm going to get that force back. Okay? Everybody all right with that idea? Okay? That means the boat will move less. It doesn't actually change a whole lot what I do. Okay? I push on the boat and the water, and it pushes back. Okay? The difference is the boat doesn't accelerate as much because I'm accelerating the boat and the water underneath it. Okay? And so it doesn't move away from me as much. But this is totally possible. Okay? Using Newton's third law. Okay, so let's look at this as a very, very simple example of Newton's third law. Okay, so I'm out in space and I've got myself with a mass with my suit. okay, of 92 kilograms, okay, and the mass of the spacecraft is 11,000 kilograms, all right? I push on the spacecraft with a force of 36 newtons, okay? Can I find the acceleration of myself and the spacecraft? Okay, force on the spacecraft is going to equal the mass of the spacecraft times the acceleration of the spacecraft. Do you agree? I'm the only force. We're out in space. If I push on the spacecraft, that's the only force. So it's the net force. Okay, so I would totally be able to calculate the acceleration of the spacecraft simply by dividing both sides by the mass of the spacecraft. So I'd have my positive 36 newtons divided by 11,000 kilograms. Okay, is that pretty small? How long does it last? How long will the spacecraft accelerate at that rate for? Okay, the velocity imparted by the acceleration will last forever. But the acceleration can only last as long as the force is being applied. So I push on the spacecraft, but the instant I'm not touching the spacecraft anymore, there's no force on the spacecraft anymore. Whatever velocity I imparted to it while pushing on it is all it has. It's not going to continue to accelerate. There's no force to make it do so. Okay? But that tiny little change in its velocity is there. Okay? And when we're talking about the spacecraft, that tiny little change in velocity can be a big deal if it has a long way to go, which, spacecraft generally do, right? This is why, NASA scientists, especially the people who are in like the course calculating departments, they have to consider every little thing. If they're off by even a fraction of a meter per second, like let's say we're talking about New Horizons, okay, the spacecraft that went to Pluto, okay, it did a gravity assist around Jupiter, which means it circled Jupiter and used Jupiter's gravity to get it going faster. Okay? They had to shoot it off at the right angle so that it would meet up with Pluto 5 years later or whatever it was. Okay? It was a ridiculous amount of time. Okay? So it's going on that course for 5 years. If they're off by even a couple of meters per second, do they miss Pluto entirely? They do. That's why rocket science has the reputation it has. Okay? It is exacting. If you are off by even a fraction of a little tiny bit of a meter per second, okay, you could be talking about missing your target by a huge amount. Okay, so those kind of things are important. All right, now, could I also calculate the acceleration of the astronaut? I could. Okay, so this one came out to like positive 0.004, no, 0.003 meters per second squared. Now, the force on the astronaut, okay, equals the mass of the astronaut times the acceleration of the astronaut. So if I divide both sides by the mass of the astronaut, I'll have the acceleration. So that'll be negative 36 newtons. Why is it negative? Well, the astronaut pushed on the spacecraft. That force was defined as positive. So the force on the astronaut is opposite. Has to be, because it's what the ship did in response. Okay? We push on the spacecraft in a positive direction, the spacecraft pushes back in a negative direction. Every action has an equal and opposite reaction. Okay, so divide that by 92 kilograms. Okay, so we got 36 divided by 92, and we get 0.39 meters per second squared, and it's negative. Well, that's a squared. Okay? So moving away. Here's what you need to take away from this. I think we talked about this back when we watched Woody go off into space. Okay? If you're an astronaut and you're doing an EVA, what they were doing, that is moving around in space with no tether, okay? Carry a heavy tool with you. Because if you were to get separated and not run out of fuel or something, you could throw the tool. Because if you throw the tool, you exert a force on the tool. And what does the tool do? It exerts a force back on you, okay? Causing you to accelerate in the opposite direction that you throw the tool. Okay? Now you have to be careful about how you throw the tool. because you're in space. If you throw it like this, okay, like overhand like that, its force is going to be backwards on your hand, and you're going to cartwheel, okay, through space, okay, because of the direction of those forces. Now, if you put the tool, your center of mass, and kind of do a chest pass with it, okay, then the force will be directly backwards on you, and you won't tumble as much, okay? Does everyone kind of follow me there? So now, if you ever become an astronaut, you can remember that Mr. Carrera gave you this life-saving advice, okay, that you will never have to use. That would totally never happen. All right, questions on how that works? So this is just illustrating a very basic example of forces acting in pairs. Every action has an equal and opposite reaction. I push with positive 36, the ship pushes back with negative 36. Okay. Now, our accelerations are very different because the masses are very different. That's the other kind of important thing there. Okay, so that was what we just did there. Okay, okay, walking. So in order to walk, okay, so when I walk forwards, which way am I pushing? I'm exerting a force backwards and down. Everybody walks differently, right? Like when I'm walking, my head stays pretty level, okay, which means I'm mostly exerting a force backwards when I walk, but you know, some people are kind of, right, and they walk a little bit like this, they push a little bit more downwards, so there's a little bit more upwards force, that's why the train goes like that, okay? It's every reaction has an equal and opposite reaction. So, if I'm walking that way and pushing backwards, what's pushing me forwards? The floor, which is attached to the ground, which is the earth. So, my acceleration forwards is considerable because I have a very small mass. Am I accelerating the earth backwards? Totally. I'm totally accelerating the earth the other way. Does the earth care? Does it make a negligible or noticeable effect? Okay, here's the mass of the earth. 5.98 times 10 to the 24 kilograms, okay? That's my mass. It's not really, I would never tell you my mass, but we'll say that that's my mass, okay? Are those at all comparable? Not at all, okay? Does my walking make any difference to the earth? What if everybody walked the same way? What if I lined everybody up? Everybody on Earth. And made them all walk in the same direction? Would that make a difference? No. Even if you took all 7 point whatever billion people there are on Earth, okay? Or whatever it is, it's a large amount of people, okay? That mass is still negligible compared to that number, okay? And the amount of force that could even be exerted is ridiculous, okay? However, Nike made an ad about this in the Super Bowl. I can't remember now how many years ago it was. And it was about the Earth had stopped rotating. And so they needed to get the Earth rotating again. So everyone would walk or run in the same direction, and that would start the Earth rotating again. I mean, I look like a crazy person most of the time, but I looked like a totally crazy person when that ad came on because I'm yelling at the TV about how stupid that whole idea is. And the worst part of it, Bill Nye was in it, which for some reason gives it scientific credibility, even though the guy's an idiot. But what, you know, oh, whoops, that was out loud and recorded. But yeah, okay. So he's not a real scientist. He plays one on TV. Okay, I'm going to show you this ridiculous video. Compared to the mass of the Earth, that would just never work. And in fact, we'll do a little activity one day that only takes about 15, 20 minutes, okay, that actually mathematically analyzes what would happen if everybody jumped at the same time, which is essentially the same idea.
Over the course of the Earth just existing, do you think that its rotation has changed?
It absolutely has, but that's more to do with the moon than it is like the Earth itself. So when the Earth and the Moon first formed because of that impact of Theia, okay, the Moon and the Earth were way, way closer together. So the Earth spun around, a day was about 6 hours. Okay? And the Moon was going around the Earth several times a day. Now it takes 28 days for the Moon to orbit the Earth once. Okay? So the Earth's rotation actually gets slower every year because the Moon gets further away. So eventually, the Earth will become tidally locked to the Sun in the same way that the Moon is tidally locked to the Earth. Okay? It'll get far enough away that it can't cause the Moon or cause the Earth to continue rotating. So there's this effect that the Moon has. As the Earth rotates underneath it, it's attracted to the Moon. But because the Earth spins faster than the Moon rotates, that force that the Moon exerts pulls the Earth backwards and actually slows its rotation ever so slightly. Okay? But when you multiply that by 4.5 billion years, the effect is quite noticeable. So yeah, our period of rotation gets smaller by fractions of a second every year. Okay, we got a couple other videos that are a little funnier than that. Okay, so in all of those funny videos, okay, what we're seeing is Newton's third law. A bullet has an incredibly small mass. So the force of those expanding gases exerts a huge force, okay, on that tiny mass, and thus it accelerates greatly. Okay? But the other part of that equation is what happens to the firearm when those expanding gases push on the firearm as well. Okay? And of course that is going to push back on the firearm. The smaller the firearm, the greater the kick is going to be because its mass is smaller. So you have to be prepared and ready for that. Okay? If you've ever seen somebody shooting a pistol like this, that is so not real. Okay? If you were holding a pistol at arm's length with your elbow locked like this, all that it would do is come back and get you in the nose. And on top of it, the shells tend to eject this way, which means that the hot shell would hit you on the head, okay? Which is dumb. They're designed to be fired this way. Okay? There's nothing cool about this. Okay? Yeah. Okay. Here's another application of Newton's third law. How many of you have seen, the person who's driving down the Deerfoot with their Honda Civic, towing one of the rented U-Haul trailers at 130 kilometers an hour? Meanwhile, there's stickers all over the thing that say maximum speed 80 kilometers per hour. Okay? So these trailers, the small rental ones, typically don't have electrical actuated brakes. Okay? Most trailers, if you have a truck, you plug them into the truck and the truck can electrically actuate the brakes on the trailer, okay? Which is important because if you try to stop as the lead vehicle and you don't have brakes on the trailer will obey Newton's first law. And it will continue to try to move forwards at the velocity it was moving when you, in front of it, tried to stop, which will cause the trailer car to jackknife, okay? The trailer will try to pass the car. You typically see this with semi-trucks when it gets icy. Okay? If the semi-truck, the tractor part, okay, the truck part, hits the brakes, it typically has enough mass that it will begin to slow down. The trailer, especially if it's empty, has very little mass, and it will continue to try to go around. Okay? Because it doesn't have enough mass to make friction to slow it, it continues to follow Newton's first law and will come around and close up like a jackknife. Okay? That's why it's called that, right? Because of Newton's first law. So what U-Haul or whoever designs the trailers did is they used a action-reaction actuator, which means there's a spring in the hitch. Okay? So you put the hitch on the ball, okay? And when you, as the lead car towing vehicle, slow down, the trailer continues to move forward and it pushes on the tow vehicle, which pushes back, compressing the spring, which actuates the brakes. Okay? So they actually use Newton's third law to actuate brakes that are spring-loaded, not electrically actuated. Okay? And it does make them a bit safer. But you have to remember that the size of a lot of the vehicles towing these is very small, and people pack a lot of crap into those trailers and make them very, very heavy. Okay? Which generally doesn't end well if they're going really fast and towing them and they have to stop suddenly. Okay, has anyone ever towed a trailer? Yeah, okay, like it's a lot different. Driving when you're towing a trailer is a lot different. And not just because you're much slower to accelerate, it's actually more slowing down. Okay, you feel the towing, the thing you're towing push on you. You can actually feel that a lot of times. Okay, all right, so that's just another application, Newton's third law there. Okay. I would like you guys to copy this question down. We're going to look at this question in terms of Newton's third law. Okay? The math is still going to break down to Newton's second law, but it's a Newton's third law question. Okay, so for this question, I've got 3 boxes. I know all of their masses, and I know that the boxes accelerate at 1.5 meters per second squared because they're a system. Okay? And we know that in a system, all parts have the same acceleration. Okay? The question tells me that an applied force, so the hand, pushing on A, causes all 3 boxes to accelerate. They want me to find the force that box C exerts on box B. So they want a force that is inside of that system. Okay? Why would box C push on box B? C comes after B. Why would it push on box B? What is B doing to C? Pushing on it. So if B pushes on C, C has to push back on B. Would you agree? How do those 2 forces relate? So B is going to push on C, and because of that, C has to push back on B. How do those 2 forces relate? They're equal but opposite. They are an action-reaction pair. All right? So here's what I need to do. I need to break this question down into individual boxes. I'm being asked about an individual force, not a system-wide force. Okay, so even though it's valuable for me to know that the acceleration of the system is 1.5 meters per second squared, sorry, because it's the acceleration of each part, beyond that, I can't treat this as a system. I'm looking for a force inside of the system on an individual part. Okay, so which box is my best bet for solving this? I'm trying to find the force that C exerts on B, keeping in mind that this is frictionless. Which box is my best bet for finding the force that C exerts on B? It's a force acting on B, right, that they want me to calculate. So, should I use box B? Okay, well, let's have a look. Let's draw the free body diagram for box B. Okay, B is 10 kilograms. Okay, this is the force they want me to find. The force of C on B. Okay, it would push back on B, right? It would be backwards. What's the other force acting on B? A, right? Pushing forwards. All right, so I got the force of A on B going to the right. I got the force of C on B going to the left. Do I know that force? Does it tell me anywhere in the question what that force is? It doesn't. Do I have any way to calculate it? Force of A on B? I have no way to calculate that force. In this question, I am not given enough information to calculate this force. I can calculate the net force on B. Okay, I can go F net, okay, equals M times A, 10 times 1.5. Great, the net force is 15 newtons forward. That doesn't help me. I don't know either of the 2 forces that add up to that number. I'm being asked to find one of them, and I don't know the other one. And I have no way to get it. I can't use box B at all. I don't know enough information. But box C on the other hand, has a mass of 5 kilograms. How many forces are acting on box C? Just one. I mean, gravity and normal force are there, but they cancel, so they're not important. Okay? Only one force is acting on C, and it's B. Okay? And what did we just say a minute ago about that force? This force and this force are equal, but opposite. But equal is the important part. If I can calculate one of them, I know the other one. I just switch the direction. Everyone okay with that logic? Okay, so now I know that. How do I get that force? F net. This is the only force acting on this object. Does that make it the net force? It's a vector sum of all forces, right? That's the only force. That's the net force. Do I have the mass and the acceleration? I do. Okay. So F net equals the force, the force of B on C. Okay? That means mass times acceleration equals the force of B on C, which means 5 times 1.5, which is 7.5 newtons forwards. Okay, so the force B exerts on C is 7.5 newtons forwards. What's the force that C exerts on B? 7.5 newtons backwards. How much math was there in that? One calculation, that's it. Okay? I mean, yes, we had to figure this part out, but that didn't involve any calculating. Okay? I just had to do vector sum of all forces. Oh, that was easy. There was only one force. That means that force is the net force. Okay? That's how a Newton's third law problem goes. In Newton's third law problems, you do Newton's second law math, and then go, all right, I found a force that's equal to another force, or that is part of an action-reaction pair with the force I want. Okay? And I just recognize they're equal, but opposite in direction. Okay? That's what most Newton's third law problems come down to, is doing some Newton's second law, and then going, I want the opposite, and do that. Okay? Questions on how that one worked? Just so you know, pretty much every year on the unit exam, I have a 2-box question. Okay? This is a 3-box question. That makes it actually harder than the one I'm going to put on the test. Okay, so for the same situation, now I want you to calculate the force that B exerts on A, keeping in mind that you can use the information you got in the last question. Okay, so that would be that the force C exerts on B is negative 7.5 newtons, okay, and that the force of B on C is positive 7.5 newtons. Okay, now you've got to calculate the force that B exerts on A. Nothing in box 1. Which box should you use? Okay, do you know any of the forces acting on A? You don't know how hard the hand is pushing, right? And you're being asked to find how hard B pushes back on A. You don't know any of the forces acting on A. You can't use A. So which box should you use? B. You should use box B because the force that A exerts on B is equal but opposite to the force that B exerts on A. You're being asked to find the force B exerts on A. Okay? You can find its action-reaction pair using box B. So there's your tip. Start with box B. Draw a free body diagram of box B. and recognize that as in the last question, the acceleration is 1.5 meters per second squared. Okay? All right, so we determined we can't use A because we're being asked to find this force, the force of B on A, but we don't know what the force of the hand is. So I don't know enough forces about A to use it. But I do know that for box B, which has a mass of 10 kilograms, that there is a force backwards of 7.5 newtons from C, and that there's a force forwards from A. That force is the action-reaction pair to the force they want me to calculate, the one that B exerts back on A. Okay? So there's only two forces acting on B, and I know one of them. And I know the net force acting on box B is 15 newtons in a forward direction. What's the other way to calculate net force? I just used M times A. What's the other way?
Vector sum.
Vector sum of all forces. So that means that F net equals negative 7.5 newtons plus the force of A on B. Can I calculate the force of A on B? All right, so I'm going to have F net minus negative 7.5 equals the force of A on B. And that's going to be 22.5 newtons in a positive direction, because this was 15 newtons. 15 minus negative 7.5 is 22.5 newtons forwards. Okay, I only have two significant digits, so that should actually be 23 newtons forwards. Okay, but you get the idea there. All right, now, if I had given that to you, just box B, as a Newton's second law question, you would have laughed at it, because it's ridiculously easy, right? I knew the net force, and I knew one of the two forces. It was an elevator question, essentially, okay? Because there were only two forces acting on it. But because I throw in those other boxes, it gets complex, because I have to see all those action-reaction pairs. That's what makes Newton's third law questions tricky, even though they're really just Newton's second law questions. Right? We'll look at a few more of those, not tomorrow, but Thursday, because tomorrow we're going to do our lab on friction. All right, so make sure you've got your SparkView apps on your phones ready, okay? Because we're going to be, oh, sorry, no, wait. We're not going to use those SparkView apps. Okay, we don't need it. We're using something else. Okay, so make sure you've got your Newton labs submitted for 8:30 a.m. That is when they are due.